Hi, I'm Caso and this is La Fisica che non ti aspetti. Today I want to tell you about a story that I wrote about in my book, Radioactivity. But don't be fooled by the title though, the book is in Italian only. Let's talk about a story that, starting from the most harmful effects of radioactivity, has led, as sometimes happens, to an improvement in the conditions, in this case, the working conditions, of many people. But let's start with this little one. This is a glow-in-the-dark star that you can buy at any stationery store. You know how it works, right? If you shine a light bulb on it or put it in the sun, it will accumulate a certain amount of energy that will be released over the course of a few minutes and make it glow in the dark. This is a phenomenon known as phosphorescence, and I won't go into it here. Spoke about it in another video in Italian that I may consider translating if you think it would be useful. In this case, the luminescence lasts only a few minutes because the energy source is no longer present when we put the star in the dark. So, once the accumulated energy is exhausted, there is nothing left for it to do but to fade away. It is a very different matter when we talk about this. This keychain is also luminescent, but with one important difference. Its brightness never fades except on huge timescales, on the order of years. I bought it about 2 years ago and it does not seem to have reduced its brightness appreciably. It is certainly not a beacon in the dark, but if you are in a dark room, you can see it very clearly. The blue color is only given by a filter, and this item can be purchased from several online stores in different shades and colors. But why does it never turn off? The reason is simple. The power source in this case is internal to the small device and can provide power for years and years. You may have guessed that this has something to do with radioactivity, and of course you're right. The energy source of this luminescence is the tritium contained within it. Tritium is a rare isotope of hydrogen and is the heaviest among those found in nature, having mass number 3, that is, 1 proton and 2 neutrons in the nucleus. Now, saying that tritium occurs naturally is almost an exaggeration since its relative isotopic abundance is reported as traces. There are few natural phenomena that lead to its formation, and among them, the most common is the nuclear reaction between a nitrogen-14 atom and a fast neutron from cosmic rays. One of the possible outcomes of this reaction is the formation of a carbon-12 nucleus and one, precisely, of tritium. Tritium is almost completely produced artificially, and in this case the nuclear processes are various. The neutron activation of lithium-6 or lithium-7, which could be employed in the formation of this isotope as fuel for nuclear fusion reactors. The fission of boron-10, which has been employed for BNCT, boron-neutron capture therapy. The capture of a neutron by a nucleus of the smaller isotope deuterium, as it happens in some nuclear reactors and others. However, these are processes that take place inside nuclear reactors or in particle accelerators, so they are purely synthetic in nature. Tritium is the element of contention regarding the Fukushima water release. Tritium is rare because it is unstable, and it is the only radioactive isotope of hydrogen. In fact, it decays beta-, transmuting into helium-3, which is stable instead. The electrons produced by this decay are the energy source of my keychain and all similarly luminescent objects that have been produced since roughly the 70s. The process is similar to that of the more common fluorescence of glow-in-the-dark stars. The decay electrons excite the valence electrons of some fluorescent substance, presumably phosphor, and bring them into an excited state, from which they then descend to an intermediate and long-lived or metastable one. When the electrons finally return to the fundamental level, they emit the luminescence we know. Is this process dangerous? I mean, I keep a keychain containing a radioactive isotope in my pocket. Should I be worried? Fortunately, not. Since the few electrons emitted, and surely there is not much tritium in this keychain, are all either absorbed to produce fluorescence or simply absorbed by the plastic wrapping it. I'm going to demonstrate. Here is my Geiger counter. It is certainly not a super professional model, but it will do the trick. Here the meter is measuring the environment, and you see how the value of counts per minute indicated by the arrow hovers around a value of a few tenths. And leaning on the keychain does not detectably change the count. Okay, so tritium does not pose a problem, but before the 70s, what was being done? Did people use phosphorescent substances such as the little stars, or did they simply not make watches and trinkets with luminescent components? Or did they use something else? Let me introduce you to my most recent eBay purchase. This hand is from an old watch with a fluorescent dial, and indeed it glows in the dark, just like tritium, although the intensity has diminished a great deal now. Let's say, though, that things are a tad different in this case. Let's move on to the demonstration. Just resting the plastic case with the hand is enough to make the counts per minute increase significantly. That's a sweet difference, isn't it? Also, consider that this object is presumably more than 50 years old. If it had tritium in it, which is obviously not true given the radioactivity levels, it would be almost completely depleted by now, after more than 5 half-lifetimes. Nope. Here, we are definitely dealing with something whose activity is definitely higher. But what danger does it pose to me? I certainly don't want to stand with my face pressed against the case, but the radiation emitted by this element, which is radium-226, is mainly of the alpha type, and alpha radiation is easily shielded from virtually everything. In fact, the Geiger reading is due almost entirely by the gamma rays that are emitted by the isotope and its decay daughters. Although radium-226 decay chain includes only alpha and beta type decays, many of the daughters can be in an excited state at the time of formation and emit a very rich gamma spectrum. However, just moving the case a few centimeters away is enough to bring the reading back to values similar to those in the environment. See how the lows and counts decrease dramatically until they return to levels indistinguishable from environmental levels? So keeping this little thing on display doesn't pose a risk to anyone. At least, not until I take it off. And here we come to the story I wanted to tell you. Radium was used a lot for hands and fluorescent objects for the same reason that tritium was used later. The source of the fluorescence is inside the paint. But applying the paint created quite a few problems for those who had to perform this task. It was predominantly women who painted the watch hands, which is why the story is known as the Radium Girls affair. Unfortunately, in order to make the brush tip finer and achieve smaller details, the female workers would lick it, often after washing it in a very perfunctory manner. As a result, they were ingesting a modest but not insignificant amount of radium. They were told that radium was harmless and that was the best way to thin the brush tip in order to save time and materials. But this was a deliberate exposure to a risk, since the danger of radium was well established by the 20s. When Marie Curie discovered radium in 1898, she identified it because she had observed that in a mineral known as pitchblende or uraninite, which, as you may imagine, contains uranium, there was a radioactive element that belonged to the chemical group of calcium. This means that by taking a periodic table of the elements, it is found in the same column. Marie Curie arrived at this deduction by observing that its chemical reactivity was very similar to that precisely of calcium. Elements that belong to the same group react very similarly with each other. And this is the origin of the problem for the Radium Girls. Radium behaves similar to the calcium of which bones and teeth are made of. The result of ingesting radium was to have it attached to the mandible, the jaw, and teeth. Internal exposure to radium alpha radiation and its decaying daughters led to numerous cases of injury, ulcers, and tooth loss in less severe cases, and anemia, weakened bones, and necrosis in more severe ones, symptoms of a clear chronic radiation syndrome. And about a dozen women even lost their lives. What makes this case particularly important was the fact that the Radium Girls sued the companies they worked for in court and, not without difficulties, succeeded in obtaining compensation, but more importantly, the recognition of their condition as an occupational disease. The process set up by the Radium Girls led to the enactment of occupational safety laws that had hitherto been absent, so their situation allowed many people after them to enjoy safer working conditions. Even in the radium watch industry, licking the tips of brushes was stopped, and the protection of painting personnel was greatly increased. This affair also led to a much greater awareness of the effects of radium on our health. For example, by discovering that radium-228, which is definitely rarer, mostly of synthetic origin, is much more dangerous than radium-226 because of its half-life of less than 6 years and the type of decay, beta-, which is more harmful even for sources outside of the body. A somewhat macabre trivia about this fact: one of the pieces of evidence brought by the Radium Girls in court to prove that their condition was due to exposure to radium-226 was that the inventor of radium paint, Dr. Sabin Arnold from Sochotki, died from exposure to the paint he invented. Well, I hope you enjoyed the story and the experiments. I thank you for watching and see you in the next video. Kuzo out! Oh, come on, I know you want to know what happens if I remove the case. You better not handle the lancer with your bare hands, lest you risk picking up traces of paint on your fingers. But the difference is huge, since the alpha particles are much less shielded now that there is no protection.